Anyway, hi, I'm Leah. Thanks for being here. If you've ever heard about me before, it's probably because of one of my open source projects, the most popular of which are these ones. I'm also a member of the CSS working group. I used to work for W3C. Now I'm mostly spending my days writing a book about CSS for O'Reilly, which hasn't come out yet, but it will by the end of this year. And also at the end of this year, I'm quite changing my life, and I'm starting at MIT as a grad student, which is quite exciting and scary. So enough about me. Let's move on to more interesting things, like how color works on screen. So let's assume this is a white pixel, or at least this is how most people imagine a white pixel. Most people think of pixels as some squares that can have like millions of possible states for every color, but actually the reality is a bit different, and the white pixel does not quite look like this. It looks more like this. And these three are called subpixels. So every pixel that you see on your screen is actually divided into 3 subpixels, one for red, one for green, one for blue. And in our modern LCD screens, they actually... This broke again, I think? Oh, okay. They actually look more like this. In CRT screens, they're a bit different. Their shapes are different, but the general idea is still the same. Every pixel is formed by 3 subpixels. Their order might also be different. The blue might be first instead of the red being first. But the general idea is the same. You might be wondering, how on earth is this a white pixel? This is just red, green, blue. This doesn't look like white at all. And yes, when you see it in this kind of size, it doesn't look like white. But when it starts getting smaller and smaller and smaller, it starts looking a bit more like white. And if this was actually a proper screen with proper subpixels, it wouldn't look gray now. It would look more like white, because that's the general idea. Your eye that can't tell that level of detail, so when those subpixels are really small, your eye tends to blend the colors together. And if you blend lights that are blue, green, and red, you end up seeing white. And this is how subpixels look for different colors, because depending on what color you're trying to make, different parts of this, different subpixels light up at different intensities. For example, if you want to make orange, which is fully red and has some green, as you can see, the green subpixel is not completely lit. This is how it looks when it's completely lit up. So it's like halfway through. And the blue subpixel is completely off, because orange doesn't have any blue. And you can see how they look for even more colors. By the way, my slides are online, so you don't need to keep any notes or try to completely understand every single bit of code or anything. And all the demos are there. So this is our friend, the subpixel again. And usually, everything I say today has exceptions, especially these days. But usually, we use 8 bits to store every channel, 8 bits for red, 8 bits for green, 8 bits for blue, which is exactly why they usually go from 0 to 250, because when you have 8 bits, you can have 2 raised to the 8 different states, which is 258 different states, which is 0 to 250, which means every pixel is 24 bits, which is 3 bytes. So if you have an uncompressed image with absolutely no compression and no transparency, because transparency is an extra channel, this is exactly what its size looks like. The number of pixels multiplied by 3, and that's the number of bytes it has. You can test it out if you try like a BMP image, which is completely uncompressed. And subpixels are quite interesting, because I'm sure all of you have zoomed in text on the screen and have noticed these weird colors that its pixels have on the edges. Let's change this text to something nicer. So actually, the reason there are these weird colors on the edges of text is because in these days, anti-aliasing for fonts is usually done through subpixels. There's also grayscale anti-aliasing, which is just lighting up different shades of black. But usually it's done through subpixels. And if you gray out the whole thing, the subpixels look like this. This gives you a much better degree of control, so the outlines look smoother. But if you zoom in, it looks weird, because when you light up different subpixels, and not all of them at the same time, you get a color. You don't get black or gray. So, for example, if you see here, this channel is lit up much more than this, so you end up getting this weird orange. And as you move it, as you move the text, the subpixels you have to use for anti-aliasing are different, so the colors change. And you can notice that the pixels used on the left are more reddish, and the pixels used on the right are more bluish, exactly because you have to light up the first subpixels to do anti-aliasing on the right, and the last and the third ones, and the second and third ones to do it on the left. You can see how it looks on grayscale. So let's move on to color in code, which is basically color in CSS and color in JavaScript. There will be quite a bit of JavaScript. I hope that's okay. So if you think about RGB, it's basically a coordinate system with 3 coordinates, red, green, and blue. And they go from 0 to 50-50. So if you think about it geometrically, all the possible colors you can achieve with RGB are basically a cube. And this point is white, because to achieve white with RGB, you need all the components need to be at their maximum, to 50-50 usually. And you can see the different colors. The most fully saturated bright colors are on the edges of the cube. Don't use those colors. They're usually pretty ugly, like this one or this one, Kian. However, on screens, when we're using color pickers, for example, to select a color, we can't really use a cube. There was a website at some point that tried to enable users to select colors 3-dimensionally. It didn't work very well, because our screens are 2-dimensional. So we can't really use a cube to select colors. So the next best thing, when you need to represent a 3-coordinate system in 2 dimensions, is to flatten one of the dimensions and show a plane with the other 2, which is what this type of color picker usually does. So you can alter one of the 3 dimensions, and you can see all the resulting colors here. So when red is, for example, 36, as it is here, these are all the possible colors you can achieve. And you can move this and see all the different colors you can get if you keep these constant and you change red. And you can change the coordinates here so that you keep green constant, and you can see all the possible colors that you can achieve with specific values of green. And same with blue. So, as you probably know, you can use this sort of notation in CSS. I'm pretty sure you've used it millions of times. You just specify the 3 coordinates. You can specify percentages if you feel like it, but it's still kind of not very useful. There's also this one, which is even more complicated than using decimal numbers for RGB, because it's equally complicated as RGB, because humans are not really used to thinking about colors in that way. We don't say, I want a color that has some red light mixed with half green light. We say, I want an orange. So RGB is not exactly intuitive. And hex RGB is even less intuitive, because not only you have to think in RGB terms, but you also need to convert decimal to hex in your brain, and vice versa. So yes, we know that the first 2 digits are the red channel, and the second 2 are the green channel, and the last 2 are the blue channel. And we've probably internalized by now that FF means 250-50, and 00 means 0, because those are the maximum and the minimum values we can get. But can we really say off the top of our head what 5A means? That it's 90. And it's actually this color, which doesn't really show as nice as it does on my screen over there. I was worried about that. Yeah. Oh well. So, even though we've internalized some values, some hex values and what they correspond to in decimal, most of us don't really understand hex as well. But hex is actually pretty simple. We have 10 digits for decimal. These are the numbers we're used to. And hex digits start off as the same 10 digits. They are just more. And we have 16 hex digits. That's why it's called hex. Hex means hexadecimal, which is related to 16. And you might be wondering, how does a digit look after 9? Well, you probably know the answer already because you've used it. But after we run out of digits of that sort, we start using letters. And if it wasn't hex and it was a number system with base, 32, we would use even more letters. We could use the whole alphabet. If we wanted the number system with base 24 plus 34, we can use the whole alphabet. But we don't need to use the whole alphabet with hex. We only need these extra digits. And apart from that, if you think of how it uses 16 digits instead of 10, everything else works exactly the same way. So until 9, hex and decimal are exactly the same. Then in decimal, after 9, we run out of digits. So we need to use 2, which is how we reach to 10. But in hex, we haven't run out of digits yet. So we can use A, and B, and C, and D, and E, and F. And F, as you can see, is up to 15 in decimal. So after F, we do run out of digits in hex as well. So we start using 2. So 10 in hex is 16 in decimal. And so on. Eventually, at some point, we will run out of digits in hex as well. As the first of the two. So we will end up having to use, there it is. So they work exactly like regular digits. After 9F, we need to increment 9. We have more digits to do so. So it goes to A0. And of course, 2 50/50s FF. And an easy way to convert 2-digit hex numbers to decimal is to multiply the first digit times 16, because that's how many 16s you have, and add the last digit. So, for example, in the 5A we had before, it's basically 5 times 16 plus 10, because A means 10, so you reach 90. However, you usually don't really need to think about that. You just need to have access to a console so you can do it, so you can type a line of code and convert them. And it's actually pretty easy to do it with JavaScript. To convert decimal to hex, you just need to call toString on it with a parameter. It actually accepts a parameter for what number system you want to use. If this parameter was 2, you would convert to binary, which is also quite interesting. And there are 2 ways to convert to decimal. These are 2 different ways. It's not code with 2 lines. So you can either use the second parameter in parseInt, which is the number system you use, and it's actually faster than the second way. Or you can prepend 0x to the number and prepend a plus to the whole thing so that JavaScript converts it into a decimal number. And even though this is not very useful when you're writing code that converts arbitrary hex values to decimal, it is really useful when you want to do something like this. So I'm not sure if you can see the text code, but like the quickest way, if you have a hex code that you want to convert to decimal, is to just type something like this, and you just get the result immediately. And of course, instead of having only 6-digit hex numbers, we can also have 3-digit hex numbers, which expand to the 6-digit one you saw at first. So, for example, this one. Keep in mind that the colors are actually lighter than they appear there. Would convert to this. And many people have requested in the CSS working group that we should have 2-digit hex numbers as well. Like this, for example. And this was not accepted. It doesn't seem like we're ever getting those, because what does this expand to? It's quite ambiguous. Because most people who requested this expected it to expand to something like this. But if we follow the same rule as 3-digit hex codes, it should expand to something like this, which is much less useful. Nobody would want this. It's how often do you run into colors that have the first 3 digits the same, the last 3 digits the same? So yeah, we gave up on that. And we also got some really awful color names in CSS 2.1, of which the ones I've actually used are white, black, gray, and red, basically, and sometimes yellow. The rest are kind of useless. How many of you have actually used any of the other ones? Okay, maybe orange as well. But they're awful. Why? So, yeah, CSS 2.1 colors are basically the RGB notation, which is confusing because it's RGB and people don't think like that. Screens think like that. People think about color in a different way. Hex notation, which is even more confusing because it's both RGB and that we have to think about hex as well, and color names that are mostly useless. So at the times of CSS 2.1, we were kind of screwed when it came to color. And you can actually test that out if you try this game I wrote for this talk. So this game, if you press play, it gives you a color to guess, and you have to type any CSS color to guess it. And it's kind of worth it to try to guess a color. I mean, if you have a laptop, you can just load it up right now and try it. This is the URL. And it's interesting to try to guess a color with RGB, and then to guess one with hex, and then to guess one with HSL. And it's interesting how much less time it takes you, assuming you both understand RGB and HSL. It's really interesting how less time it takes you when you try to do it in a more natural way that HSL provides. And I don't know if I'll manage to do it on stage because it's kind of stressful right now, but I'll try to do it. So it's a bit light and saturated, so these should be lighter. And lighter. It's getting there. It needs a bit more green. Yeah, we're close. Yeah, it's getting there. You actually don't have to guess the full color the way it is. You just need to find something that's close enough. Like 99.2 at least, I think. This was easier when I tried it without an audience. Okay. You can see why RGB is confusing. I've done this millions of times, and it's still quite difficult. I think I'm close to giving up right now. Yeah. I don't like giving up. Oh, well. Sometimes you have to, because we don't have infinite time. But you see, I've been trying for a minute and a half, and I still can't guess it. And I generally am quite interested in color, so in the next few slides, sometimes we're going to see methods added to a simple JS color class. You know, JavaScript doesn't really have classes, so I've included quotes, otherwise people will lynch me afterwards. But yeah, so this is the main idea. You want to be able to create colors either by providing arguments or by providing an array. So it checks if the first argument is an array or else, and if it's an array, it sets the RGB property, which is actually not a property, it's a getter and setter that we'll see in the next slide, to the first 3 elements of that array. And then it tries to get alpha, because alpha could be either the 4th element of that array, or it could be a second parameter. We want to be flexible. Or if it's not an array, it's pretty easy. We just set red to red, green to green, blue to blue. And then we set alpha to whatever it was, either this parameter or whatever we have from this line, or just 1 if we haven't provided an alpha at all. And we also have 2 getters and setters, because sometimes we want to manipulate RGB all at once with an array instead of setting the 3 channels individually. So if we try to get it, it returns an array with red, green, and blue. If we try to set it with an array, it assigns the first element to red, the second one to green, and the last one to blue. And if all the methods that most of the methods we're going to see are going to be added at some point here. And this allows us to create colors in any of these ways, or even in this way, because they have default values. So by default, it's just black, and then we can assign values to it. Or even by this way, because we don't even need to set green, because it's 0 by default. So that's pretty flexible. It's kind of useless at this point, because it just creates and stores a color and doesn't do anything useful with it at this point. But throughout the stock, we're going to add useful things to it. And let's move on to HSL for a bit. So in CSS Color level 3, we got a slightly more intuitive way to think about color. And this is also three-dimensional. The first dimension is a hue, which basically means what is my color reddish, or is it orangish, or is it yellowish, or greenish? Like, what's the main hue of the color? And then how close it is to gray. That's what saturation is. How close is our color to gray? And then lightness, which is how close it is to black or white. So this is also a color picker. So you can see the different colors that can be generated from this. For example, let's suppose we want to choose a muted, slightly dark pink. We can instantly find that it's here, and then it's like, this is much more intuitive than compared to how people think about color, because that's what you usually say. I want a muted dark pink. You don't say, I want a color that has some red with even less blue. Who talks about colors this way? And this is the notation you use in CSS, which I'm sure you've all used. And you can change the coordinates and see how it ends up being. And HSL is actually three-dimensional. It's a coordinate system with 3 coordinates as well, but different one. It's actually something called cylindrical coordinates, because the first coordinate is not it is an angle. So we can provide an angle of 400 if we want to. It just wraps around it. It's equivalent to 40. And I think it actually works in browsers as well. So 400 is the same as if we subtract 360 from it, which is 40. Same thing. But in reality, it's not actually a cylinder, which is what you end up with if you have a circle and 2 other dimensions. It ends up being more like a cone, because as you move towards a lightness of 0 or a lightness of 100, then you get even less possible colors. As you can see here, as I move towards 0, there are much fewer possible colors I can get. Same as I move towards white. I don't get this spectrum that I have here. It's fewer and fewer colors that I can generate, and when lightness is 100, I can only generate 1 color, white. Same with when it's 0, it's only black. And yeah, I'm not going to try this again for HSL, but trust me on this, it is much faster. However, HSL is not perfect. We tend to think that lightness actually means lightness, as in how light the color is, right? However, as you can see in this example, it's not exactly close to how we perceive lightness as humans. These 2 colors have exactly the same lightness values. It's yellow and blue. Are they equally light? Should they have, for example, both the same color of text on them to be readable? Absolutely not. So, and you can see this a little bit with gray as well, although it's not as visible as the previous example. Gray is actually, it should be halfway through white and black, but it's actually closer to black. And that happens because HSL is not perceptually uniform. When it comes to color space, perceptual uniformity means that you can determine how similar 2 colors are by measuring the distance between them. For example, here, the distance between them, you can see that it's the same, goes from 0 to 50 and then from 50 to 100. And in RGB, it's also the same. This would be 0, 0, 0, 0. This would be 250, 50 times 3. And this should be 127 times 3. So it's completely halfway through. However, the problem is RGB is not perceptually uniform. A small change by the same amount in RGB can end up with colors that look slightly similar or colors that look very similar. And HSL isn't perceptually uniform either, because HSL is just RGB. It's not a different color space. The only color space that is supposed to be, well, one of the color spaces that we're used to from color pickers and stuff that's actually perceptually uniform, or at least it's designed to be perceptually uniform, even though it's not 100% that way, is Lab. If you've ever used Photoshop, you might have seen the Lab color system. That's a color system designed by the Color Consortium to have this property, to be perceptually uniform. But RGB is not even close. You can see this here as well. This is not HSL, this is just RGB. Both of these colors have exactly the same distance from the middle one. But are they equally similar? These two are much more similar than this one than the second is with the third. And this is the reason why lightness isn't exactly a good measurement of how light a color actually is, how light we perceive a color to be. So if we end up having some color that looks like this, we have a random color, we don't really know what it is, it's a variable, we set our background to it, and then we need to figure out a color that contrasts sufficiently with it so that we put text on it and it's readable. So many people would end up doing something like this. But that won't work, because if you see how the lightness getter is defined, and this is how it's defined, this is how HSL lightness is computed, it just gets the maximum of the 3 RGB coordinates and the minimum and averages them. That's it. If you have lots of green, it counts the same towards lightness as a lot of blue, even though our eyes are much more sensitive to blue than they are to red than they are to green. So we perceive green as much lighter than red, and red is much lighter than blue. So no, not all RGB coordinates are born equal. Some of them are more equal than others. And if we want to get something that even remotely represents how light a color is, we need to take that into account. So this won't do very well. Instead, there is another measurement called relative luminance, and you can see this formula is both present in CSS Colors Level 4, and it's also in an earlier specification called Web Content Accessibility Guidelines for calculating color contrast. This is the measurement you use when you want to calculate color contrast between two colors to make them sufficiently accessible. So, as you can see, it's not actually very complicated. You just make some small transformations on every channel. This is exactly the same for red, green, and blue. But then, what you return is weighed. So as you can see, blue is multiplied by a smaller number than green is than red is. And you can see here how it works for different colors. For example, blue has a luminance of 7%, which is much more close to how we perceive colors than lightness is. And it doesn't have the same problem as yellow, for example, which has the same lightness. So according to our code here, it would end up having white text. But the luminance of yellow is 93%, which is much closer to how we perceive color. And this is the formula for color contrast, which is basically we calculate the two luminances. We add a little bit to them so that we don't end up dividing by 0 in case they're 0. Because, of course, black has both lightness and luminance of 0, and white has both of them to 100%. So we add a little bit to them, and then we get the ratio, and that's color contrast. So I've written an app here that you can use to calculate color contrast and whether it passes the accessibility guidelines, and you can even use any sort of CSS color. In CSS Color Level 3, we also got semi-transparent colors, both for RGB and for HSL. So the same one in HSL would be 0 and 100% here and 50% here. All right, HSLA. So we've used that as well. But have you ever wondered how this sort of thing works? Because our screens cannot display transparent pixels, really. Everything needs to be composited into actual opaque pixels. Because what would a transparent pixel look on a screen? Would you see the behind of your screen, like what's inside it? So everything needs to end up being opaque pixels. This is just convenience. It doesn't correspond to any sort of hardware alpha channel. There's no alpha subpixel. It doesn't make sense. So we use something called alpha blending. Which is an algorithm that was invented by Porter and Duff in as early as 1984. And simple alpha blending looks like this. And we basically multiply every component of the color on top with its alpha, and we add every component of the color behind it multiplied by its own alpha, and also multiplied by 1 minus the alpha of the color above it. Because if you have 60% on the color above, then you can only see 40% of what's behind, so you need to multiply by that 40%. And the alpha of the resulting color, it always increases, because if you have a semi-transparent color and a semi-transparent color under it, obviously you cannot get a color that's less semi-transparent than what you have. And it increases by this amount, which is the alpha of the color under it multiplied by 1 minus the alpha of the color above it. And something quite similar to alpha blending is how you mix two colors together. For example, if you want to get the average of two colors, in which case the weight here would be 50%. So you multiply every component by 0.5, for example, or whatever the weight is, and then you add the component of the other color multiplied by the opposite, like 1 minus the weight. And in SAS, you can do that with the mix function, and it just takes two colors and a weight parameter based on how much you want of the first color. So if you specify 90% here, you get 90% of this color and 10% of the second color. And this is actually used when the browser is doing a gradient. And when it's opaque colors, you get what you expect. But what happens when you do a gradient between white and transparent? Well, at this point, we stop being able to see our code until, I made it black. So now we can see it. However, this is not a gradient from white to transparent as we would expect it. You might be wondering what's wrong with it. It becomes more obvious what's wrong with it if we see how it should be properly. Yeah, and it should look like this. So you can see the difference here. There is some gray here that shouldn't exist. And the reason this happens is that transparent is just a shorthand to RGBA 0000. So as our white is transitioning, our white is transitioning from opaque to transparent, it's also transitioning from white to black, because transparent is transparent black. And the CSS Color Level 3 spec was updated at some point, and it specified that the transition needs to happen in what's called a pre-multiplied RGBA space, which means every color is stored after it's multiplied by its alpha channel, which ends up in much smoother transitions, because transparent is not anymore transparent of a specific color, it's just transparent. So the perceived effect, this is not how the colors are actually stored, but the perceived effect looks like this. If you interpolate between white and transparent, you end up with a gradient that looks like this. And if you want to do the same effect in a browser that doesn't support pre-multiplied transitions, like Firefox, even though I'm using the nightlies here, it still doesn't support it. Instead of using transparent, you can use actual transparent white. And now we got the same gradient. And we also got some extra colors, some extra named colors, but they're not exactly evenly distributed. And they're also kind of stupid. They're too long. Some of the names are incredibly silly. Some of them even border on the racist. And some of them are just insane. I'm not making this up. So those are not very useful. What we did get that's useful is another color keyword. So have you ever noticed that when you use a border without a color, it just gets the text color? I can change the text color and it just adapts. And box shadow has also the same property. If I use a box shadow without a color, it just gets the text color. Text shadow is the same as well. If I use a text shadow without a color, you can see how this got blurred because it's the same as specifying lime here. So until CSS 2.1, these were just rules and specific properties that if the author doesn't specify a color, you just get the text color. In CSS, in level 3, this kind of behavior got its own keyword and its current color. So we can use it even in properties that don't use current color as a default. So for example, if we want to have a background with stripes that are transparent and the current text color, we can do something like this and then make the background size smaller. And we end up with something like this. And if we change the text color, it just works. And it's basically the first variable ever to be supported in CSS, because you can just change the text color and current color updates everywhere. So these are the colors we got in CSS3. HSL is not perfect, but it's better. Okay, RGB and HSLA were badly needed. We got more color names that are mostly useless, and we got current color. So what's in store for CSS level 4? I'm finishing. Gray became a function, and the gray keyword is equivalent to gray 50%. But now we can also adjust this, and we can get all sorts of grays. So we don't even need the two-digit hex codes anymore, because we can have something that reads much more naturally. And even though this is not supported by any browsers yet, you can implement it yourself in SAS with just these 2 lines of code. And it works exactly the same way as it will when it's supported by browsers. This is exactly the same syntax. We will also get 4-digit hex codes in CSS in level 4, which are the same as 3-digit ones plus alpha, and 8-digit ones, which are exactly the same as 6-digit ones plus alpha. So this is the opaque color, this is with alpha. So you don't have to convert your hex colors anymore to make them transparent. And we will also get the amazing color function that allows us to provide lots of adjusters and adjust colors. And this is especially useful when you're using variables, because red could be a variable, because we're also getting custom properties in CSS, which are basically variables. And we can also use shade to mix it with black. And we can even use blend to blend it with another color. And there are all sorts of different adjusters we will be able to use. So we can do all sorts of things with the color function. Tint and shade we can already implement it in SAS. And if you use Bourbon, it's already included. And tint and shade just mixes with the color with white and black, which is actually pretty useful in making it lighter and darker. Much useful than lighten and darken. And we're also getting this HSP color system that many people use in Photoshop, and until now we couldn't use it in CSS, and will be called HWB, which stands for hue, whiteness, blackness. It's kind of weird, but it's the same thing. Hue is exactly the same as HSL, and the other 2 coordinates are exactly the same as what we have in Photoshop. So this is a summary of what we will get tentatively in CSS Color Level 4. The syntax might change at any point. This is very unstable right now. And you can use this polyfill called myth.io, which is like a preprocessor, but it tries to support these early drafts, so you can use the syntax today. I didn't write it. And this is some code that you can use to take advantage of the browser to parse any supported CSS color, but I don't think I have enough time right now to go through it, but you can see it in my slide. Thank you very much.